In this lesson, I want to apply the work kinetic energy theorem to answer a very simple question. We have a 40 kilogram block that's being pulled by a constant applied force of 150 newtons. The force is applied at an angle of 20 degrees relative to the displacement. We'll say the object displaces um, 10 meters. So the question is, what's the final velocity of the object? There's a coefficient of friction of 0.25. The object starts from rest. In the previous lesson, we came up with an equation for the work kinetic energy theorem that says the net amount of work done on any object is equal to its change in kinetic energy. And because we define kinetic energy as the quantity 1/2 mv squared, then we can find the final velocity in the case where an object starts from rest as being the square root of 2 times the net amount of work divided by the mass. Okay, so let's see if we can find what the net amount of work done is. Let's make a free body diagram. Pointing upward is not just normal force, there's also a vertical component of the applied force. So we'll say this is N plus Fa sine theta. Back to the left is force of friction, call that mu times N. Downward is the force of gravity, mg, and to the left is the applied force component, Fa cosine theta. So forces along the y-axis are going to cancel out. The only way they could cancel out is if the normal force is equal to mg minus Fa sine theta. And we're going to need that expression to help calculate for the frictional force. So the work done by the normal force we know is 0 because the angle between the normal force and the displacement is 90 degrees. Also, the work done by gravity for the same reason is going to be 0. So what we need to do is calculate the work done by the applied force, and we need to find the work done by the force of friction. So let's start with this. Work done by the applied force should be equal to the magnitude of the applied force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between them. So in this case, it's 150 newtons multiplied by 10 meters times the cosine of 20 degrees. So 1,500 times cosine 20 gives us a value of about 1,410 newton meters, or 1,410 joules. Now for work done by friction. That's equal to the magnitude of the friction force times the magnitude of the displacement times the cosine of the angle between those. Well, the angle between those is 180 degrees, and cosine of 180 is -1. We need to make one more substitution here. In place of normal force, we'll substitute. So we have mu times, there's what we're going to substitute for normal force, mg minus Fa sine theta. So mu times mg minus Fa sine theta. All right. So that's the force, and then we need to multiply that times the displacement, and then all of that times -1. So if we want to plug in the numerical values, this is 0.25 times 40 times 9.8 minus 150 sine 20, and all that multiplied by 10. Of course, this is kilograms and meters per second squared, but a kilogram meter per second squared is a newton. This 150 was also newtons, and the 10 is meters. So in the end, we know we're going to end up with newton meters or joules as the numerical value. Grab a calculator, maybe take this piece by piece. When we multiply the sine of 20 times 150, we get 51.3. 40 times 9.8 gives us 392. So 392 minus 51.3 gives us 340.7. We need to multiply that times 10, and we need to multiply that again times 0.25. And that gives us a total work done by friction of 851.75 joules. Negative 851.75 joules. So the net amount of work is 1,410 joules minus 851.75 joules. And we'll round off and call that 558 joules of net work. So the final speed, notice we're not using any kinematics here to get a final speed. We're given an initial speed of 0. We're given a displacement of 10 meters. And that's it. We never calculated the acceleration. We don't know anything about time. I suppose from our free body diagram we could use Newton's laws to find an acceleration, and then from there use the kinematics equation. But based on the work kinetic energy theorem, we can get around that. And we can say that the velocity is equal to the square root of 2 times the net amount of work divided by the mass. So in this case, it's the square root of 2 times 558 joules divided by 40 kilograms. Now let's check the units on this one. Remember that a joule is the same thing as a Newton meter. So when we say joules per kilogram, we can call it Newton meters per kilogram. And then recall also that a Newton is a kilogram meter per second squared. So we have kilogram meters per second squared times meters, all divided by kilograms. And a meter times a meter gives us a meter squared. So we have is meters squared per second squared. But notice we're taking the square root of all this. And so in the end, we'll have meters per second, and that checks out, given that we're trying to solve for a velocity. So grab your calculator and see what you get. So when I work it out, I get about 5.3 meters per second as my final answer. So there's just one example of how we can apply the work kinetic energy theorem to problems involving force and displacement and work. Thanks for watching.